Hi everybody, welcome back to the Feynman technique. This is part 3 of the video where I solve this integral using Feynman integration. In part 1, we showed a cool representation for the arctangent function. In part 2, we used that to get this result. Technically, you should not say that this is equal to anything. This integral diverges. But you can kind of get the result that it's equal to negative I over 4, and we're going to be using that. Don't put that as the answer on any sort of test because you'll get a 0 for that. But the math says that that's what it's equal to, so we're going to use that. Anyway, now comes the part where we actually use Feynman integration. So we will start in the usual manner by creating a function of t, and it's going to look almost like this thing. It's going to be the integral from 0 to infinity of cosine tx over pi squared minus 4x squared dx. And we will note that f at 0 is going to equal this thing, which we're calling negative I over 4. All right, and of course, f at 1 is going to give us back our original integral I. All right, what next? Well, as is often the case in Feynman integration, the next step is going to be to take the derivative of on the left and right hand side of this thing with respect to t. So we're going to get f prime of t equal the integral from 0 to infinity of the derivative with respect to the partial derivative with respect to t of the integrand. So what's that going to give us? Well, we're going to get a negative, let's see, we're definitely going to have this pi squared minus 4x squared in the denominator. And we're definitely going to have a sine tx. And we're definitely going to have an x. We're going to have an x, and it's going to be negative. So that's what it is. F prime of t is equal to negative integral 0 to infinity of x sine tx over pi squared minus 4x squared. Now, let's do something to this. Let's put a parentheses around here, and let's multiply the top and the bottom by x. And you can totally do that. That's just multiplying the entire thing by 1, so it's valid. And then next, let's bring this negative inside. All right. But let's also multiply this by 4. But if we multiply it by 4, we have to divide by 4. All right, so this is still valid. This is still f prime of t. Now what I'd like to do is put a parentheses around this and introduce a pi squared term inside that parentheses. Okay, well, what did that have the effect of doing to the entire integral? This is dx, by the way. That added 1/4 the integral from 0 to infinity of pi squared sine tx over pi squared minus 4x squared times x. So we added that. We have to subtract it, or else the equation is not valid anymore. We wouldn't have f prime of t if we didn't do that. So that's going to be minus pi squared over 4 times the integral from 0 to infinity of, let's see, sine tx over pi squared minus 4x squared times x. All right. So you notice that cancels with this. That was the whole point. And what are we left with? We're left with 1/4 the integral from 0 to infinity of sine tx over x. Well, I've shown many times on this channel that the integral from 0 to infinity of sine tx over x dx is equal to pi over 2 for t greater than 0. Important, t greater than 0. If t equals 0, this thing is 0. Okay. So, as long as t is not equal to 0, this whole thing right here, this entire thing is just going to be pi over 8. So we're just going to erase that and literally put pi over 8 in its place. Because as long as t is not equal to 0, that is pi over 8. So f prime of t is equal to pi over 8 minus this. Okay. Now let's let t approach 0. What do we get? We're not evaluating t at 0. Very important distinction there. If you evaluated t at 0, that thing would not be there. This thing would go away. It would not be pi over 8. If t was 0 beforehand, this would go away. T at 0, f prime of t at 0 is 0. But the limit as t goes to 0 of f of t is equal to pi over 8. And we're just going to call this f at 0, just for simplicity's sake. But we know that we're actually taking the limit as t goes to 0. So I'm just going to write f at 0. And just know that that's not technically true. We're taking a limit as t goes to 0. All right, so don't leave that in the comments. They'll be like, no, f of 0 is not pi over 8, it's 0. I know. Okay, so let's continue with our Feynman integration. If this is our f prime of t for t not equal to 0, what is f double prime of t? Well, f double prime of t would be the derivative of this thing with respect to t. This pi over 8 would drop out, and we'd just be left with negative pi squared over 4 times the integral going from 0 to infinity of cosine tx over pi squared minus 4x squared dx. And you'll notice this right here, this integral, is simply f of t. Okay. So we'll just write that as f double prime is equal to negative pi squared over 4 times f of t. All right, that's a differential equation. All right. We don't need anything else except for that differential equation now. We need that differential equation. In order to solve for f of t, we need this differential equation, and we need these values right here. Okay. So we can erase everything else. We know that once we solve this differential equation and we plug 1 into it, we get the value of our original integral. All right, since this is not a channel on differential equations, I'm not going to show how to solve this. I will say it's not that hard. If you have any experience with differential equations, this is not a particularly hard one to solve. All right. It's going to have this general solution. We'll have the general solution where f of t is equal to some constant a times e to the I pi over 2t plus b times e, this is a constant, some constant b times e to the I pi over 2t, except that's negative now. Okay, so that's our f of t. And go ahead and verify that f double prime of t, if you took two derivatives with respect to t of this, that you'd get negative pi squared over 4 times the original thing. That it would satisfy this equality right here. If you took two derivatives of this, you would get negative pi squared over 4 times this. All right. I'm not going to show that, but trust me, it's true. All right. So there's our f of t. And we have some values for f at certain points, so that's good. But how we need to use, oh, this is f prime at 0. We need to somehow use f prime of 0 is equal to pi over 8. So let's find f prime of t. F prime of t is going to be equal to a times I pi over 2 times e to the I pi over 2t plus b times minus b times I pi over 2 times e to the negative I pi over 2t, right? Oops. Yeah, I did that right. All we did was bring down this constant in front of that a. We brought down this constant in front of that b. And we still have, all right, so that's valid. So now let's use f of 0 equal negative I over 4. All right, so f of 0 is equal to negative I over 4, which in turn is equal to this thing when t is 0. Well, what's that? That's just going to give us a plus b. All right. So negative I over 4 is equal to a plus b. All right, now let's use f prime of 0 is equal to pi over 8. What do we get? So f prime of 0 is equal to pi over 8, which in turn is equal to this thing at t is equal to 0. Well, if t is equal to 0, these exponential terms just go away. So we're left with a times I pi over 2 minus b times I pi over 2. All right. We don't need this part anymore. Let's divide both sides of this by pi. This becomes a 1. This goes away. This goes away. Now let's multiply both sides by 2. We get a 2. This just becomes an I. This just becomes an I. Now let's divide both sides by I. This becomes A. This becomes minus B. This becomes a 1. This becomes a 4. Multiply the top and the bottom by I. We get I over negative 4, or just negative I over 4. Adding these two equations together, you will get negative I over 2 is equal to 2a. So a is equal to negative I over 4. If a is negative I over 4, I hope it's obvious that b would be 0. And then b is equal to 0. So, plugging a is equal to negative I over 4 and b is equal to 0 into our f of t, we are left with f of t being equal to a, which is negative I over 4, times e to the I pi over 2t. And now we know that our original integral is equal to our f, our f of t evaluated at the point t is equal to 1. So what's that give us? I is equal to negative I over 4 times e to the I pi over 2 times 1, or just e to the I pi over 2? Well, what is e to the I pi over 2? That is simply the complex exponential form of I. So this e to the I pi over 2 is simply I times I. This I combines with this I, multiplies it to produce a negative 1. So we get a negative 1. This negative cancels with that negative, and we are left with I being equal to 1/4. And that's it, guys. There is that integral solved with Feynman integration and the use of this technically not true, but yeah, sort of kind of true result that we derived in part 2. And that's the same answer that Maths 505 got when he did this integral with contour integration. So the fact that we got the same result kind of validates this a little bit, because if this wasn't true, we would not have gotten the right answer. So it's kind of a valid. It kind of vindicates this equality right here. But anyway, that's it. I hope you enjoyed that.